Hello friend, welcome to this quiet moment we are going to share together. Before we go anywhere, before we travel across the vast distances of space, I want you to just be here right now in this room. Find a comfortable position. You might be sitting in your favourite chair or perhaps lying down. It does not matter where you are as long as your body feels supported. Let your shoulders drop, unclench your jaw, let your hands rest gently, close your eyes or just soften your gaze, letting the world around you fade a little bit into the background. Let us take a deep breath together. Breathe in slowly through your nose, feeling the cool air filling your lungs, expanding your chest like a balloon. Hold it there for just a second. Now breathe out gently through your mouth, letting all that air escape, carrying with it the stress and the noise of your day. Let's do that one more time. Breathe in deeply, inviting calmness in. Side, and breathe out, letting go of everything else. Now that you are still, let your imagination drift. Imagine that today is the 29th of October in the year 2025. On Earth, it might be a regular Wednesday. People are rushing to work, drinking their coffee, checking their phones, and worrying about the small things. The world down here is noisy. It is full of traffic chatter and endless notifications. But where we are going, there is no noise. We are going to lift off gently, leaving the atmosphere behind. Imagine rising up, floating weightless. The blue sky turns into a deep velvety black. The stars are not twinkling here. They are steady, burning bright and clear in the endless dark. It is silent here, a silence so deep and so profound that it feels like a heavy blanket wrapped around you. This is the silence of the cosmos. As we float here into this peaceful darkness, turn your attention to the center of our neighborhood in space. There it is, the sun. Even from this distance, 150 million kilometers away, it is magnificent. It is a perfect sphere of glowing plasma. It is not just a yellow circle. It is a living, breathing engine of the solar system. If you could hear it, it would be roaring with the power of 1 billion nuclear explosions happening every second. But here in the vacuum of space, it is just a beautiful, blinding light. Today, on this specific date in October 2025, something special is happening. It is not an explosion, it is not a collision, it is a moment of perfect quiet geometry. Astronomers and scientists call this event solar conjunction. It sounds like a complex technical term, but the idea is actually very simple and very beautiful. Imagine a straight line drawn across the solar system. On one end of the line is you on Earth. On the very far end of the line is the planet Mars, the red planet. And directly in the middle of that line, blocking the view perfectly, is the sun. Usually the sun is a spotlight. It lights up the planets so we can see them. It gives us warmth and energy. But right now, during this conjunction, the sun changes its role. It stops being a spotlight and becomes a wall. It becomes a massive burning curtain. Imagine standing in a theatre. The stage is huge, but the heavy velvet curtain has been pulled shut. You know the actors are behind it. You know the scenery is there. You know the story continues even though you cannot see it. That is what the sun is doing right now. Mars is currently passing behind the sun from our perspective on Earth. The red planet has slipped behind that blinding curtain of fire. For a few weeks, Mars is invisible to us. We cannot see it with our eyes, and more importantly, we cannot speak to it. Think about the robots we have sent there. The rovers rolling across the red dust, the landers sitting still on the rocks, the satellites orbiting high above the Martian surface. Usually we talk to them every day. We send them commands. We ask them to take photos, to drive forward, to dig into the soil. They send us messages back, telling us the temperature, sending us pictures of the alien sunset. But today there is only silence. The sun is so powerful and it gives off so much energy and charged particles that it disrupts our radio signals. If we tried to send a command to a rover right now, the sun would swallow that message. The signal would get lost in the noise of the solar wind. It would be like trying to whisper to a friend across a room while a jet engine is blasting between you. So the engineers on Earth have done something rare in our modern world. They have stopped talking. They have sent their final commands weeks ago, telling the robots on Mars to be safe to stand still and to wait. And then they hung up the phone. Right now, behind that giant burning curtain of the sun, the machines are on their own. Mars is alone. I want you to feel the weight of that isolation, but not in a scary way. Feel it as a moment of peace. The constant flow of data has stopped. The endless stream of ones and zeros has paused. It is a cosmic holiday, a time for the universe to take a breath. Visualize the sun again. It looks like a solid disk of gold hanging in the black void. It looks calm, but we know that on its surface giant loops of fire are dancing. Solar flares are erupting, throwing matter out into the dark. It is a chaotic, violent, beautiful shield, and hiding safely behind that shield is an entire other world. What is happening back there in the shadow of the sun? Is the wind blowing on Mars? Is the dust settling on the solar panels of our quiet rovers? Are the stars shining down on the rusty rocks? We do not know. We cannot know, not right now. We are just the audience sitting in the dark theatre waiting. The curtain is down. The play is happening in secret. This is the mystery of the solar conjunction. It reminds us that we cannot control everything. It reminds us that sometimes, even with all our technology, all our antennas, and all our cleverness, nature is still bigger than we are. The sun is the king of this system, and when it decides to stand between us and our neighbours, we must respect it. We must be patient. Let that feeling of patience wash over you. There is no rush to see what is behind the curtain. There is no rush to send a message. There is nothing to do but wait and watch the fire. In this silence, there is a strange kind of comfort. It is a reminder that not everything needs to be seen to be real. Just because Mars is hidden, it does not mean it is gone. It is simply waiting, spinning on its axis, drifting through the dark, just like we are. Keep this image in your mind: the Earth blue and quiet, the vast darkness of space, and the brilliant sun hanging like a golden coin hiding the secrets of the red planet behind its fiery back. Breathe in the silence, breathe out the need to know, just float here for a moment in the shadow of the cosmic curtain and listen to the quiet hum of the universe. To understand why the scientific community is currently holding its collective breath, we must first look at the traveller itself. We call it 3-Eye Atlas. In the vast catalogue of things that float through the dark, names are usually just numbers. They are coordinates in a database tracking dull rocks that drift aimlessly for billions of years. But 3-Eye Atlas is different. It is not behaving like a rock, it is behaving with purpose. And right now it is heading toward a specific point in space that physicists call perihelion. To understand the stakes, we have to strip away the complex mathematics and look at the simple geometry of our solar system. The word perihelion comes from Greek roots. Peri means near and helios means sun. Quite literally, it is the point in an orbit where an object comes closest to the star it is circling. For a comet or an asteroid, perihelion is a time of violence. As a rock gets closer to the sun, the heat rises to thousands of degrees. Ice turns instantly into gas, creating the long, beautiful tails we see in the night sky. Rocks can crack and crumble under the intense gravitational stress. It is a trial by fire. Most objects survive it, but they do not enjoy it. They swing around the star and retreat back into the cold comfort of deep space as fast as they can. However, for 3-Eye Atlas, perihelion is not just a hazard. It represents an opportunity. This brings us to a concept in orbital mechanics known as the Oberth effect. While the name sounds technical, the concept is something you can understand if you have ever watched a skier on a mountain or a child on a playground swing. Imagine a skier standing at the very top of a massive steep hill. This hill represents the gravity of the sun. When the skier pushes off and starts to slide down, they naturally pick up speed. Gravity is pulling them down, making them go faster and faster without any effort on their part. By the time they reach the bottom of the valley, they are moving at their absolute maximum speed. The wind is rushing past them and their momentum is enormous. Now imagine that this skier wants to shoot up the next hill to reach an even higher peak than the one they started on. They need extra energy. The most efficient moment for them to use their poles to push to add their own energy to the mix is exactly at the bottom of the valley, right when they are moving the fastest. If they push while they are still slow at the top of the hill, it does not help much. But if they push when they are already moving at breakneck speed at the bottom, that extra energy is multiplied. It flings them forward with incredible. This is the Oberth effect. In spaceflight, engines are more efficient when the spaceship is moving fast. We believe 3-Eye Atlas is doing exactly what that skier is doing. It is falling into the gravity well of our sun, allowing the massive pull of our star to accelerate it to speeds that are hard to comprehend, hundreds of kilometers per second. It is diving toward that bottom point, the perihelion. If 3-Eye Atlas is an artificial craft, as some of the data suggests, it will not just coast around the sun. It will wait for that exact moment of closest approach, the moment of maximum speed, and then it will fire its engines. It will push at the bottom of the valley. By doing this, it can steal energy from the sun's gravity. It can change its trajectory sharper than any natural rock ever could. It can gain enough speed to shoot out of our solar system entirely, or perhaps slow down enough to enter a stable orbit around Earth. This maneuver is the hallmark of intelligent navigation. It is the most efficient way to travel between the stars. And this leads us to the great irony of our current situation. Logic dictates that this is the most critical moment in the entire history of our observation of this object. If 3i Atlas maneuvers, if it changes course, if it fires an engine, it will happen now during perihelion. This is the climax of the event. This is when we would finally get the proof we have been chasing. We should be watching it with every camera, telescope and sensor we possess, but we cannot see a thing. This is the physics of shadows. Usually we think of a shadow as a place where light is blocked, but in astronomy you can be blinded by too much light just as easily as you can be hidden by the dark. Because 3i Atlas is approaching perihelion, it is from our perspective on Earth right next to the sun in the sky. It is lost in the glare. Pointing a standard optical telescope at it right now would be like trying to spot a firefly hovering next to a stadium floodlight. If you pointed the delicate lenses of the Hubble Space Telescope or the James Webb Space Telescope directly at the sun to look for this object, the focused light would destroy their sensors in seconds. We are effectively blind. The object has entered a zone of silence. We have tracked it for months as it fell through the dark, calculating its path, arguing over its nature and waiting for this week. And now that the week is here, now that the skier has reached the bottom of the hill, the screen has gone blank. We are currently in a waiting game that is excruciating for the scientists involved. We know that right now, millions of kilometers away, the object is enduring the maximum heat of the sun. We know the gravitational tides are pulling at it, trying to rip it apart. If it is a loose pile of rubble, a standard comet, the sun might destroy it completely. It might disintegrate into a cloud of dust and gas, and we will never see it emerge on the other side. If it is a solid rock, it will swing around and come out on a predictable path, proving that it was just a strange asteroid all along. But if it is a ship, and if it uses the Loeb effect to change its speed, it will emerge from the glare on a completely different path than the one it went in on. It will come out of the sun's shadow behaving in a way that physics cannot explain without the presence of an engine. So we wait. We are like people standing outside a closed door listening to a storm rage on the other side. We know something is happening in the furnace of the perihelion. We know that the laws of physics are being tested to their limit. But until 3i Atlas drifts far enough away from the sun for us to safely point our telescopes again, we are left with nothing but theory and suspense. The skier is in the valley. We are waiting to see if they crash or if they fly. The phone rang in the control room of the Keck Observatory in Hawaii. It was not a dramatic alarm, just a standard rhythmic ringing that cut through the quiet hum of the cooling fans and the soft clicking of computer keyboards. Outside the summit of Mauna Kea was pitch black, sitting high above the clouds, surrounded by the freezing thin air that makes this location one of the best places on Earth to look at the stars. Inside, however, the air was warm and thick with the smell of stale coffee and the nervous energy of discovery. The astronomer who picked up the phone was not expecting the news he was about to hear. On the other end of the line was a colleague analysing the spectral data, the chemical fingerprint of the object that was currently speeding away from our sun. To understand why this phone call changed everything, we first have to understand how we touch the stars without leaving the ground. We cannot fly to this object and scrape a piece of it off to study in a lab. Instead, we look at the light. When sunlight hits an object, the object absorbs certain colours and reflects others. By breaking that reflected light into a rainbow, a process called spectroscopy, we can read the barcode of the object. Every element in the periodic table has a unique signature. Hydrogen looks one way, carbon looks another. What the team was looking for was the standard recipe of the universe. Most rocks in space, especially asteroids, are what we call primitive. They are leftovers from the early days of our solar system. They are like the sweepings from a bakery floor, a little bit of flour, some sugar and some dust all mixed together in a messy, chaotic lump. In these space rocks you expect to see a lot of iron. Iron's the great common dust of the cosmos. Where you find rock, you usually find iron. And where you find iron, you almost always find its chemical cousin nickel. In nature, iron and nickel are like inseparable twins. They are forged together in the hearts of dying stars. When a massive star explodes, it spews these two metals out into the void in a very specific ratio. Usually for every 10 parts of iron, you might find 1 part of nickel. They travel together, they clump together. To find one without the other is incredibly rare. But the voice on the phone was reporting something that did not make sense. The data from the telescope was clear, but it was telling a story that shouldn't exist. The light reflected off the object showed a strong glowing signature of nickel. It was screaming nickel. But when they looked for the signature of iron, the line was flat. There was no iron. The astronomer at Keck likely paused, staring at the screens. A rock made almost entirely of nickel with almost no iron is not just unusual. It is a chemical anomaly. It violates the standard rules of how space rocks are born. This brings us to the concept of alchemy of the void. In ancient times, alchemists tried to turn lead into gold. They wanted to purify base metals. In a way, the universe does this, but it is a messy cook. The universe likes to mix things up. Gravity pulls dust and gas together into swirling clouds. Everything gets mashed into a soup. Entropy or disorder is the rule of nature. If you pick up a random rock from the ground or a random asteroid from the belt between Mars and Jupiter, you're holding a mixture of everything that was floating around when the solar system was born. Pure things, on the other hand, are rarely natural. Think about the aluminum can on your desk. You will never find a soda can growing on a tree or protruding from a rock face. Aluminum exists in nature, but is always trapped inside other rocks bonded with oxygen in a messy reddish clay called bauxite. To get the shiny pure metal of a can, you need a factory. You need intention. You need to crush the rock, heat it to thousands of degrees and run electricity through it to strip away the impurities. You have to force the chaos to become order. This is the difference between natural and industrial. Nature is a mixture. Industry is a separation. The object moving through our solar system was displaying the characteristics of industry, not nature. It was too clean. The surface appeared to be coated in a complex organic sludge, likely baked by millions of years of cosmic radiation. But underneath that, the data suggested a dense metallic composition that was shockingly pure. If this object was a natural asteroid, it would be like walking through a forest and finding a perfect steel cube sitting on a bed of moss. The moss is natural. The steel cube implies that something or someone processed it. There is only one natural way to get nickel separated from iron, but it is a violent and rare event. It requires a planet. When a planet forms, it becomes a molten ball of lava. The heavy metals sink to the center to form a core, and the lighter rocks float to the top. In that hot, crushing center, sometimes the metals can separate slightly. If that planet is then smashed apart by a massive collision, the shattered pieces of the core might float through space. These pieces would be metallic, but even then the separation is never perfect. Iron is stubborn, it stays with the nickel. For this object to be so heavy in nickel and so poor in iron, it suggested that it had gone through a refinery process that stripped the iron away. As the team at the observatory processed this information, the mystery deepened. The universe is usually a dusty, dirty place. It is full of ice, carbon, soot, and silicate sand. It is the attic of creation filled with old boxes of junk. But this visitor was different. It was shiny in a way that spoke of a different history. The nickel without iron anomaly forced the scientists to consider uncomfortable possibilities. Was this a piece of a specific type of dead star that we have never seen before? Was it a shard from a planet that formed in a part of the galaxy with a completely different chemical recipe than our own? Or was it the product of engineering? In human manufacturing, we use specific alloys for specific jobs. We use nickel alloys when we need a metal that can survive extreme heat and resist corrosion, perfect for the hull of a vessel traveling between the stars. We purify metals because pure metals behave predictably. We remove the mess of nature to build machines that work. The phone call at this observatory did not end with a conclusion. It ended with a question mark that hung in the air like the smoke from a blown-out candle. The data was solid. The chemistry was undeniable. The object was real. But it was a piece of order flying through a universe of chaos. In the silence of the control room, looking at the jagged lines on the computer screen that represented the light from that distant traveler, the line between geology and technology began to blur. The alchemy of the void usually produces mud. This time it had produced a sword. And as the object spun silently into the darkness, moving further away every second, it took its secret history with it, leaving the scientists on top of the volcano, wondering if they had just seen a rock or if they had just seen a machine. By the time the calendar turned to April 12th, 2025, the scientific community was no longer just looking at numbers on a spreadsheet. They were looking for a picture. The Hubble Space Telescope, the old faithful eye in the sky, had been commanded to turn its gaze toward the receding traveller. Everyone expected to see a blurry dot, perhaps surrounded by a faint cloud of dust fading into the darkness of the outer solar system. What the telescope sent back, however, was not just a picture of a rock. It was a portrait of something that defied the very nature of passive drift. To understand why the image from that Tuesday in April was so shocking, we must first understand the simple rules of the road in our solar system. Think of the sun not just as a hot ball of light, but as a massive wind machine. It constantly breathes out a stream of particles and light, creating what we call the solar wind and radiation pressure. This is a physical force. It is weak, but it is constant. When a comet gets close to the Sun, the heat boils the ice on its surface, creating gas and dust. Because the Sun is blowing a constant wind outward, that gas and dust should behave like smoke coming from a campfire on a windy day. The smoke always blows downwind away from the source of the breeze. Therefore, a comet's tail always points away from the Sun. This is one of the most basic reliable visuals in astronomy. It is the rule of the cosmic ocean: you go with the flow. But the image processed on the morning of April 12th showed something that made the physicists pause and clean their glasses. The object did not have a large billowing tail like a comet. It was mostly a tight, bright point of light. However, upon very close inspection using high contrast filters, the analysts found a distinct feature. It was a narrow, focused stream of gas, a jet. The problem was the direction. The jet was not trailing behind the object, nor was it being blown back by the solar wind. This stream of material was pointing directly toward the Sun. In the context of our campfire analogy, this was like watching smoke pour out of a chimney and fly straight into the face of a hurricane refusing to bend. In the world of physics, matter does not simply choose to ignore the pressure of sunlight. Dust and gas are light. They are easily pushed. If this material was flowing toward the Sun against the solar wind, it meant it was being ejected with significant force. It was being pushed out fast enough to overcome the wind coming from the star. This observation fundamentally changed the conversation about what this object was doing. When we see a rock tumbling through space, heating up and cracking the gas, usually vents out in random directions. If a comet rotates, the jets spin around like a broken garden sprinkler, spraying everywhere. This random spraying often causes the object to tumble chaotically, changing its spin speed and direction. But this object was not tumbling chaotically. The light curve data suggested it was stable. And now we had an image showing a jet pointing in a single specific direction forward. This is where the concept of sailing against the wind becomes more than just a poetic phrase. It becomes a mechanical description. When you see a vessel on the ocean moving against the wind, you know it is not just a piece of driftwood. Driftwood goes where the water and wind take it. To move against the wind requires structure. It requires a keel to stabilize it in the water and a sail to harness the force or an engine to push through it. The image of the sunward jet provided the missing piece of the puzzle regarding the object's strange acceleration. We had already observed that the object was moving faster than gravity alone could explain. We knew something was pushing it. Now we could see the mechanism. Isaac Newton taught us that for every action there is an equal and opposite reaction. If the object shoots a jet of gas toward the Sun, the physical reaction pushes the object away from the Sun. It is exactly how a rocket engine works. You shoot fire out the back to make the rocket go forward. By shooting gas toward the Sun, this object was effectively generating thrust. It was adding speed to its departure. The gentle yet undeniable implication of the April 12th image is that of propulsion. We do not need to jump to the conclusion of little green men pulling levers to acknowledge that the physics here resembles an engine more than a melting iceberg. A natural object can certainly have a vent. A pocket of ice can explode, but for a vent to point directly at the Sun maintaining that orientation while the object travels implies a level of stability that is incredibly rare in random asteroids. If this were a simple rock, the force of this jet should have sent it into a wild spin. Imagine attaching a fire extinguisher to a floating log and opening the valve. The log would spin uncontrollably. This object did not. It absorbed the push, maintained its posture, and accelerated smoothly. This stability suggests that the mass of the object and the force of the jet were perfectly balanced, or that the object had a shape designed to remain stable under thrust. We began to view the object less as a passive asteroid tumbling through the dark and more like a ship. A ship has a bow and a stern, a ship maintains a heading. When a ship interacts with the wind and the waves, it does so with intention, cutting through the resistance rather than being tossed about by it. The sunward jet was the wake of a vessel that was not merely falling around the Sun, but using the Sun's gravity and perhaps its own internal energy to maneuver. The Hubble image stripped away the dead rock theory layer by layer. Rocks are messy. They crumble and outgas in sloppy, unpredictable ways. This phenomenon was clean. It was directional. It was efficient. The stream of particles fighting upstream against the solar light painted a picture of resistance. It was an assertion of a trajectory that defied the passive laws of planetary orbits. As the data from April 12th settled into the archives, the mental image of the visitor shifted. It was no longer a tablet of stone. It was a traveller with an engine, however primitive or natural that engine might be. It was moving with a purpose, turning its back to the star that warmed it and pushing off against the solar tide to escape back into the deep freeze of interstellar space. The silence of the data was loud with implication. We were watching a departure, not just a drift. We were watching a ship raise its sails, check its rudder, and push off from the shore, disappearing into the night with a final powerful kick against the current. To understand the true nature of this visitor, we must look beyond the lack of radio signals and face the physical reality of the object itself. When we stop listening and start measuring, the story changes from a ghost story into something far more tangible and physically overwhelming. The data coming back from our long-range sensors and gravity analysis paints a picture of something that should not exist, yet there it is casting its shadow across the stars. We are not dealing with a small piece of space debris, we are dealing with a leviathan. The dimensions alone are enough to make one feel incredibly small. The object measures approximately 5 kilometers in length. To put that into a perspective that a human mind can grasp, imagine a mountain like Kilimanjaro torn from the earth and set adrift in the vacuum of space. Or picture the entire island of Manhattan, specifically the stretch from Central Park down to the financial district, turned into a solid block of material and hurled through the cosmos. It is a size that transcends the typical scale of human engineering. When we build things that fit in our hands or buildings that we can walk through. This object is a landscape unto itself, but size is only half of the equation. The true shock comes when we calculate the mass. Based on the gravitational perturbations it causes on the dust and smaller particles surrounding it, we estimate this object weighs roughly 33 billion tons. That number is difficult to wrap your head around. It is not just heavy, it is planetary in its density. It suggests that this is not a loose collection of rocks and ice held together by weak gravity, which is what we usually find in comets or asteroids. A pile of rubble would not be this dense. This mass implies solidity. It implies a core of iron nickel, or perhaps something even heavier and more exotic that we have not yet discovered on the periodic table. It possesses a gravitational field strong enough that if you were to stand on its surface you would feel a distinct though light pull keeping you grounded. You could walk on this world. This leads us to the inevitable comparison with the ghosts of the past. We must look back at the first interstellar visitors we detected to understand why this one is so unique. First there was Oumuamua. When it passed through our solar system years ago, it was confusing. It was long and thin like a cigar, and it tumbled chaotically through the dark. It was strange, yes, but it was relatively small, perhaps only a few hundred meters long. It felt like a piece of driftwood floating in the cosmic ocean. Then came Borisov, which was clearly a rogue comet. It acted like a comet. It had a tail of gas and dust, and it behaved exactly as nature dictates a ball of dirty ice should behave. This new visitor is nothing like them. It is not tumbling out of control like Oumuamua. Its rotation is slow, deliberate, and perfectly stabilized. It is not shedding gas or dust like Borisov. It is structurally sound. It moves with the momentum of a freight train, ignoring the minor gravitational bumps of our solar system. Where the others felt like accidental tourists, this object feels like a purposeful traveller. The sheer scale of 33 billion tons moving at such velocity requires energy and momentum that dwarfs our entire nuclear arsenal. However, there is a paradox here, a contradiction that keeps astronomers awake at night. An object this massive and this large should be visible. It should reflect the light of the sun. Even a rock reflects some sunlight. The moon, which is made of dark grey dust, still lights up our night sky. But this object, it is almost invisible. The albedo, which is the scientific term for how much light a surface reflects, is near zero. It is darker than fresh asphalt. It is darker than charcoal. In fact, it absorbs almost 99% of the light that hits it. This is not natural. In nature, very few things are this perfectly black. If it were a simple asteroid, the solar wind and micrometeoroids would have scarred it over millions of years, exposing lighter material underneath. But this object remains a void in the sky. This extreme darkness leads to unsettling theories. Why would an object need to be so dark? One possibility is that the surface is covered in complex organic compounds, a thick sludge of carbon that has been baked by cosmic radiation for eons. But there is another, more artificial possibility. If you are building a vessel to travel between the stars, you might want to harvest energy. A perfectly black surface is the ultimate solar panel. It absorbs every photon of heat and light, wasting nothing. Or perhaps it is camouflage. Against the black background of deep space, a non-reflective object is the ultimate stealth technology. You would never see it coming until it blocked out the stars behind it. This brings us to the most daring hypothesis of all regarding the 33 billion tons. What if the mass is not distributed evenly? When we study the way the object rotates, there is a slight wobble. a hesitation in its spins that suggests the centre of gravity is not where a solid rock should have it. Some physicists have whispered the words hollow structure. If the object were solid rock all the way through, it would actually weigh far more than 33 billion tons given its 5-kilometre size. The density calculations suggest that while the shell is incredibly heavy and metallic, the interior might be empty. Imagine a honeycomb. Imagine a massive geode, but instead of crystals inside, there are corridors, chambers, and vast empty halls. The weight we detect might just be the hull, a protective skin of ultra-dense armour, designed to withstand the impacts of interstellar dust at light speed. If this is true, then the 33 billion tons is merely the container. This idea changes the feeling of the object entirely. It is no longer just a rock falling through space. It becomes a shell. And shells are meant to protect something inside. The silence of the object takes on a new meaning. It is not the silence of a dead stone, it is the silence of a closed door. It is the silence of a fortress. When you look up at the night sky now knowing this thing is out there, you feel the weight of it. It is a 5-kilometre long shadow. It is a mountain of metal that refuses to shine. It is heavy, it is silent, and it is hollow. It forces us to confront the terrifying possibility that we are not looking at a natural phenomenon, but rather we are looking at a container. And we are small, fragile creatures standing on the outside wondering what kind of things require 33 billion tons of armour to keep them safe or to keep them in. The room was quiet. It was not the silence of emptiness, but the heavy, thick silence of people who are afraid to speak because the truth is too big to say out loud. On the main screen, the simulation of the object's path was complete. It was a single glowing white line cutting through the darkness of our solar system. To the untrained eye, it looked like a simple curve. But to Sarah Chen and her team, that line was screaming. It was screaming that everything we thought we knew about this object was wrong. It was not a rock. It was not a comet. Nature is messy. Nature is chaotic. Nature throws rocks into the dark at random. This line was not random. It was perfect. The first thing that made the team pause was the inclination. In our solar system, the planets circle the sun on a generally flat plane like a dinner plate. Most asteroids and comets that come from deep space arrive at steep angles. They dive down from above or shoot up from below, cutting through the solar system like a needle. But this object was different. Its inclination was nearly 0 degrees. It was perfectly flat, sliding into our system on the exact same plane as Earth and Jupiter. It was hiding in plain sight, matching our level perfectly. Then came the direction. This was the detail that made Sarah take off her glasses and rub her tired eyes. Every major object in our solar system orbits the sun in the same direction counterclockwise. It is a rule of traffic set billions of years ago when the solar system was just a swirling cloud of dust. Earth. Mars. The asteroid belt, they all move the same way. But this object was moving in a retrograde orbit. It was going clockwise. Imagine standing on a highway where millions of cars are driving north and suddenly you see a single vehicle driving south, calmly weaving through the traffic without hitting anything. That is what this object was doing. It was swimming upstream against the river of gravity. But the true shock came when the computer analysed the history of the object's journey. The simulation rewound time, tracing the white line backward over the last 5 years. "Look at the encounters," Sarah whispered. The object had not just drifted into the solar system, it had visited us. 3 years ago, the object passed by Jupiter. It did not hit the gas giant, nor was it thrown off course by Jupiter's massive gravity. Instead, it performed a perfect gravity assist. It skimmed the atmosphere of Jupiter using the planet's gravity to slow itself down and tighten its curve. It was a maneuver that human engineers calculate for months to achieve with space probes. This object did it naturally. After Jupiter, it flew toward Mars. Again, the timing was exquisite. It arrived at the exact moment Mars was in position to offer another gravity assist. It used the red planet to adjust its angle, tilting its path just enough to line up with the next target. Then it swung inward toward Venus. This was the most dangerous part of the flight. Venus is deep in the sun's gravity well. To fly that close and not get pulled into the sun requires precise speed and angle. The object danced around Venus using the thick atmosphere to bleed off speed before slinging itself back out toward Earth. Jupiter, Mars, Venus. It was a grand tour. In the history of spaceflight, the grand tour is a theoretical path that allows a spaceship to visit multiple planets using the minimum amount of fuel. It requires the planets to be aligned in a very specific way, something that only happens once every few hundred years. For a random space rock to accidentally stumble into a retrograde orbit, stay perfectly flat on the planetary plane, and then accidentally execute 3 perfect gravity assists in a row, the math was impossible. One of the junior analysts ran the probability numbers. The computer churned for a moment and then displayed the result. The odds of this happening by natural chance were 1 in 300 trillion. In science, there is a threshold. If the odds are 1 in 100, it is a coincidence. If the odds are 1 in a million, it is a miracle. But when the odds are 1 in 300 trillion, it is not a miracle. It is a plan. "It is steering," Sarah said. "It is not falling, it is driving." The room seemed to get colder. The implications were terrifying. If it was steering, then someone or something had charted this course. But the final piece of the puzzle was the one that connected the present to the past. The team traced the trajectory back even further before the Jupiter encounter, before it entered our solar system. They extended the white line out into the deep black of interstellar space to see where it had come from. The line pointed like a celestial finger toward a specific region of the sky. It pointed directly at the constellation Sagittarius, specifically to a cluster of stars known as Chi Sagittarii. Sarah felt a shiver run down her spine. She knew that coordinates. Every astronomer knew those coordinates. In the year 1977, a radio telescope in Ohio detected a strong narrowband radio signal from that exact spot in the sky. It lasted for 72 seconds. It was so strong and so unique that the astronomer who found it circled the data on the printout and wrote one word in red ink: "Wow." The wow signal had been the greatest mystery of the 20th century. It was a single shout in the dark, never repeated, never explained. For decades, humanity had listened to that spot in the sky, hoping for a second message. We had been waiting for a call. Sarah looked at the screen. The velocity of the object was consistent. If you calculated the travel time from the Chi Sagittarii star system at the speed this object was moving and you subtracted the years since 1977, the math lined up perfectly. The radio signal 40 years ago had not been a greeting, it was a departure announcement. "They didn't just call us," Sarah said, her voice trembling slightly. "They sent something. The signal in 1977 was the launch flare. This object, this is the ship." The scattered data points suddenly snapped together into a terrifyingly clear picture. The low inclination was to ensure it could scan the planets. The retrograde orbit was to slow down relative to the planets, allowing for longer observation times during the flybys. The Grand Tour was a braking maneuver, shedding the massive velocity of interstellar travel so it could enter a stable orbit around its final destination. It wasn't just passing by, the trajectory ended here. The braking maneuvers around Jupiter, Mars and Venus were all designed to bring the object to a complete relative stop near the third rock from the Sun. It had travelled for decades across the emptiness of space. It had navigated the gravitational chaos of our giants. It had sent a message ahead of itself that we were too primitive to understand at the time. The object was now 3 days away from Earth, and based on the perfect path it had followed so far, it was not going to miss. It was coming to park in our driveway. Sarah typed a command to save the data, but her hand hesitated over the key. She realised that once this report was filed, the world would change. The loneliness of the human species was about to end. The silence was over. "The path is too clean," she said finally. "Nature draws in curves and squiggles. Intelligence draws in straight lines and perfect circles. This orbit is a work of art." She looked up at her team. The fear was still there, but it was mixing with something else now. "Awe. Ladies and gentlemen," Sarah said, straightening her back, "we are not looking at an asteroid. We are looking at an arrival." The most defining characteristic of the hours immediately following the great solar anomaly was not the heat nor the light nor the magnetic interference. It was the silence. It was a deep, suffocating silence that descended not upon the streets but upon the institutions we trust to explain the world to us. This was the fog of not knowing. When the data from the Sun began to defy every model of physics we had built over the last 300 years, the immediate reaction of the world's leading space agencies, including NASA, was not a burst of scientific curiosity. It was a retreat. It was a shutdown. To understand this, we must look away from the Sun for a moment and look into the human mind. Imagine a room full of the smartest people on Earth. These are people who have dedicated their lives to logic, to cause and effect, to the comfort of mathematics. They believe that if you have enough numbers, you can predict the future. Then in a single heartbeat, the numbers stop making sense. The sensors on the Solar Dynamics Observatory, or SDO, began screaming data that was impossible. The temperatures were too high. The magnetic fields were twisting in ways that should have torn the satellite apart, yet the satellite remained. In a horror movie, the scientist usually shouts a warning. In reality, when faced with the impossible, the human instinct is often to deny it. The initial response from the control centers was that the instruments were broken. It was easier to believe that a billion-dollar sensor had malfunctioned than to accept that the laws of nature were changing. So they did what bureaucracies do when they're frightened. They pulled the plug. The public feed from the SDO, which allows anyone with an internet connection to watch the sun, suddenly went dark. The official statement mentioned a technical glitch or server maintenance. But this was not a technical issue. It was a psychological defense mechanism. This is where we encounter the concept of terrestrial stupidity. This is not to say that the engineers and directors were unintelligent people. Far from it, but they were suffering from a very human limitation. We have built our entire civilization, our governments and our scientific organizations on the idea that we are in control. We organize the world into files, folders, protocols and safety guidelines. We believe that if we write a rule for something, we have mastered it. When the sun, a ball of plasma 1,000,000 times the size of Earth, decided to act with a cosmic intelligence that we could not comprehend, our terrestrial response was to try to manage it like a public relations crisis. We tried to apply the rules of an office building to a star. The shutdown of the public data streams was an act of fear. It was the equivalent of a child pulling the blanket over their head when they hear a noise in the dark. If we cannot see the monster, maybe it is not there. By cutting the feed, the organizations hoped to buy time. They wanted to have a meeting. They wanted to form a committee to decide what the sun was allowed to do. It sounds absurd, but in the face of the unknown, procedure is the only shield a bureaucracy has. However, this silence created a different kind of danger. The fog of not knowing spread to the public. Because the official sources were dark, the void was filled with rumour and panic. Without the steady hand of explanation, people's imaginations ran wild. The silence from the top did not calm the population. It confirmed their worst fears. It signalled that the situation was so bad even the experts were hiding. We must view this with empathy. The scientists staring at their blank screens were witnessing the death of their worldview. They were seeing energy readings that, if true, meant their textbooks were wrong. They were seeing a level of organised chaos on the solar surface that looked less like random explosions and more like intention. That is a terrifying thought for a scientist. Science relies on the universe being a machine. A machine has no feelings, no plans, and no intelligence. A machine just does what it is programmed to do, but if the sun was acting with intent, if the behaviour was not random, then the universe is not a machine. It is something else. It is something alive. Facing this realization causes a type of mental freeze. Psychologists call it cognitive dissonance. It is the mental pain you feel when reality contradicts your deepest beliefs. The outage at the space agencies was a manifestation of this pain. They shut down the servers because they could not process the reality of what they were seeing. They needed the universe to pause so they could catch up, but the universe does not pause. This clash between terrestrial stupidity and cosmic intelligence is the defining tragedy of the event. On one side, you have the sun performing a majestic, terrifying transformation, perhaps communicating, perhaps evolving, engaging in processes that involve energy outputs of 10 to the power of 25 joules. On the other side, you have humans worrying about stock markets' election cycles and whether releasing the data will cause a drop in public approval ratings. We stood on the shore of a cosmic ocean, and instead of learning to swim, we argued about who had the permit to be on the beach. The fog was thickest in the meeting rooms. Transcripts released years later showed that while the solar storm was raging, directors were arguing about the wording of press releases. They were debating whether to call it an event, an anomaly, or a phenomenon. They were trapped in the terrestrial mindset where words control reality. They forgot that the sun does not care what we call it. The radiation does not check our press release before it hits the atmosphere. Eventually, the SDO feeds had to come back online. You cannot hide the sun forever. When the images returned showing the impossible structures looping across the solar surface, the humiliation of the bureaucracy was complete. The silence had served no purpose. It only proved that when the true scale of the universe reveals itself, our human structures are fragile. We learned a hard lesson that week. We learned that our titles, our organizations, and our protocols are very small things. We use them to make ourselves feel safe, to feel like we are the masters of our domain. But there is a limit to what we can control. The fog of not knowing is uncomfortable. We hate it. We want answers and we want them immediately. But the universe is under no obligation to make sense to us. The fear that drove the shutdowns was the fear of admitting that we are small. It was the fear of saying, I do not know. In the end, the terrestrial stupidity was not that we didn't understand the physics. It was that we thought we should be able to understand it instantly. We lacked the humility to just stand still and watch. We were so busy trying to manage the event that we almost missed the message. The shutdown was a desperate attempt to keep the universe inside a box that it had already broken out of. And as the data finally flowed back in, we realised that the box was never real to begin with. We were just small creatures blinking in the light of a truth too big for our eyes to adjust to. This brings us to the Loeb scale. Think of this scale as a detection meter similar to the Richter scale used for earthquakes, but designed for the search for extraterrestrial intelligence. It ranges from 0 to 10. A score of 0 is just background noise, a known natural phenomenon, or a sensor glitch. A score of 5 suggests something truly interesting that requires intense scientific follow-up. A score of 10 is the landing on the White House lawn scenario, undeniable face-to-face proof. In this context, the object 3I Atlas was assigned a score of 4 out of 10. To some, a 4 might sound low. It is not a passing grade in school. But in the world of astrophysics, where almost everything we see is a 0, just a dead rock of 4 is staggering. It represents a tipping point. It means the object is so strange, so defiant of our standard models, that treating it as just a rock is actually harder than considering it might be artificial. A score of 4 screams, "Pay attention." So why did 3I Atlas earn this ranking? To answer this, we must organise the chaos. We need to line up the facts like we are counting sheep one by one to see the full picture of this anomaly. There are 8 distinct oddities that, when put together, make this object impossible to ignore. The 8 anomalies. 1. The shape extreme geometry. The first thing that puzzled astronomers was the shape. Most asteroids are somewhat round like potatoes, or perhaps slightly elongated. But as 3I Atlas tumbled through space, the way its brightness changed told us it was flat. Not just a little flat, but extreme. The ratio of its length to its width was at least 5 to 1, potentially even 10 to 1. Imagine a pancake flying through the solar system, or perhaps a long thin cigar. We have never seen a natural space rock with dimensions this extreme. It defied the standard potato rule of asteroids. 2. The shine. High reflectivity. This object was unusually bright. In astronomy, we call this albedo. Most comets and asteroids are dark, like charcoal, absorbing most of the sunlight that hits them. 3I Atlas, however, was shiny. It reflected light at an intensity that suggested the surface more like metal or shiny ice than rock. If it were a natural object, it would have to be made of something incredibly reflective to shine that brightly given its small size. 3. The local standard of rest, the origin. This is a concept that often confuses people, but it is crucial. Before 3I Atlas entered our solar system, it was sitting very still relative to the galaxy. The local standard of rest is like the cosmic parking lot of our neighbourhoods in the Milky Way. Most stars, including our Sun, are zooming through this parking lot, but this object was just sitting there waiting until our solar system slammed into it. It was like a buoy floating on a calm ocean and our ship hit it. This specific state of rest is very rare for a random rock ejected from another star system. 4. The rotation. The tumble. Most objects spin nicely on an axis. 3I Atlas did not spin, it tumbled. It was flipping end over end in a chaotic rhythm. While tumbling can happen to asteroids that have been hit by something, this specific tumbling motion, combined with its high speed, suggested that it had a high tensile strength. If it were a loose pile of rubble, like many comets are, the force of this spin would have torn it apart. It held itself together like a solid manufactured slab. 5. The lack of heat, no infrared signal. When astronomers tried to look at the object through the Spitzer Space Telescope, they looked for heat infrared radiation. They found nothing. This was shocking. It meant the object was extremely small, much smaller than it appeared based on the light it reflected. This reinforced the idea that it was incredibly shiny and perhaps very thin with a very small surface area radiating heat. 6. The missing gas, no cometary tail. This is perhaps the most famous anomaly. As a comet gets close to the Sun, the ice on its surface boils away, creating a tail of gas and dust. We looked for this tail around 3I Atlas deeply. We looked for carbon-based gases, water vapour and dust. We found absolutely nothing. It was dry. To all our senses, it looked like a stone, not an icy comet. 7. The non-gravitational acceleration. The push. Here is where the physics gets difficult to explain with natural models. As the object left the solar system, it sped up. It deviated from the path that the Sun's gravity alone would dictate. Now comets do this all the time, the gas shooting out of them acts like a rocket thruster. But remember point number 6, there was no gas. So we had an object that was accelerating like a rocket, but had no visible exhaust. It was being pushed by a force we could not see. Loeb hypothesized that it was being pushed by sunlight itself, radiation pressure, which only works effectively if the object is very thin and very light like a sail. 8. The velocity too fast. Finally, there was the speed. It entered our system at a velocity that proved it was not from here. It was unbound by the sun's gravity, but more importantly, the specific speed change it experienced as it left was smooth and continuous. It didn't jerk around like a rock outgassing in random spurts. It accelerated smoothly, exactly how a light sail would accelerate under the constant pressure of the sun. The courage of what if. When you line up these 8 sheep, the shape, the shine, the stillness, the tumble, the coldness, the lack of gas, the mysterious push and the speed, you are left with a puzzle that natural explanations struggle to solve. To force 3i Atlas into the category of natural rock, you have to invent a type of rock we have never seen before, a nitrogen iceberg or a hydrogen block, theories that eventually fell apart under scrutiny. This is where the courage of the Loeb scale comes in. Assigning a score of 4 out of 10 is an act of scientific bravery. It is the willingness to look at the data and say, the natural explanation is actually more complicated and less likely than the artificial one. It asks the dangerous question, what if? What if this was not a rock? What if the reason it acted like a light sail is because it was a light sail? What if the reason it was sitting still in the galactic parking lot is because it was a probe waiting for a star system to pass by? Most scientists are terrified of this question because of the giggle factor, or the fear of being laughed at for talking about aliens. But the Loeb scale reminds us that science is not about social safety, it is about evidence. When the evidence gives you 8 different anomalies that all point in the same direction, the most rigorous scientific action you can take is to follow that path, even if it leads you to something that changes human history forever. 3i Atlas was a visitor that knocked on our door and left before we could answer, but it left us with these 8 clues and the realization that we need to keep our eyes open for the next one. It is often said that science is a self-correcting system. We like to imagine science as a clean, straight road where new data is found accepted and then the world changes its mind. But the reality of human discovery is rarely a straight road. It is usually a battlefield, and standing alone in the middle of that battlefield, often without armour, is the figure of the dissident scientist. In the modern era, the face of this struggle is Avi Loeb. To understand Avi Loeb, you must first understand the environment he lives in. He's not a fringe theorist working in a garage. He was the chair of the astronomy department at Harvard University. He sits at the very top of the academic pyramid. This is a world of high-pressure, deep respect and very rigid rules. In this world, reputation is the only currency that matters. If you lose your reputation, you lose your ability to be heard. When Oumuamua passed through our solar system, the scientific community was desperate to classify it as something safe. They called it a comet. Then when it had no tail, they called it an asteroid. When it accelerated in a way that gravity could not explain, they invented new theories about hydrogen icebergs or dust bunnies. They were willing to stretch the laws of physics to keep the object natural. Avi Loeb looked at the same data and asked a forbidden question. What if it is artificial? By asking this, he did not just propose a hypothesis, he broke a social contract. The reaction from his colleagues was not just disagreement, it was anger. It was personal. They called his ideas dangerous. They called it a quest for publicity. But if you look closely at Avi's eyes during his many interviews, you do not see a man looking for fame. You see a man who is deeply, profoundly disappointed in his peers. This brings us to the concept of the gatekeepers. In every era of human history, there are gatekeepers. These are the people who decide what is true and what is crazy. They are not evil people. Often they are the smartest people in the room. They protect the institutions of science from fraud and nonsense. But sometimes they protect the status quo so tightly that they suffocate the truth. The story of the gatekeepers is as old as science itself. We must look back to the year 1610 and the story of Galileo Galilei. When Galileo pointed his telescope at the sky, he saw moons orbiting the planet Jupiter. This was a terrifying discovery. If moons orbited Jupiter, then not everything orbited the Earth. The Earth was not the centre of the universe. Galileo invited the philosophers and church leaders, the gatekeepers of his time, to look through his telescope. He said, "You do not have to believe me, just look." They refused to look. They argued that the telescope must be broken. They argued that the devil was putting illusions in the glass. They argued that Aristotle had already explained the universe, so looking was unnecessary. They chose the comfort of their old books over the terrifying reality of the new data. Galileo spent the end of his life under house arrest, isolated in silence, simply for suggesting that we are not the centre of everything. Avi Loeb sees himself in the shadow of Galileo. The modern scientific community does not use house arrest or prison. Instead, they use ridicule. They use the giggle factor. If you talk about alien technology, people laugh. The laughter is a weapon. It signals to young scientists, do not touch this topic or your career will die. This creates a deep loneliness. Imagine seeing something clearly, something that could change the history of the human species, and having everyone around you refuse to look through the telescope. Avi has spoken about walking into the mess halls at conferences and seeing conversations stop when he approaches. He has spoken about the bullying culture of modern academia. Why does this happen? Why is the smartest group of people on Earth so afraid of the unknown? The answer is human nature. We are terrified of being ordinary. For thousands of years we believed we were the center of the universe, geocentrism. Science took that away. Then we believed we were the only special creation of life. Darwin took that away. Now we cling to the last shield we have, the belief that we are the only intelligent civilization. We want to believe we are the smartest kid on the block. If Oumuamua was a piece of technology, it means we are not special. It means we might be like ants living on a sidewalk unaware of the humans walking past us. That is a scary thought. It is much safer to say Oumuamua was just a rock. A rock does not challenge our ego. A rock does not make us feel small. The gatekeepers use a famous phrase from Carl Sagan: extraordinary claims require extraordinary evidence. On the surface, this sounds reasonable, but Avi Loeb argues that this phrase has become a shield for conservatism. Who decides what is extraordinary? To a scientist, everything should be just evidence. By labeling the idea of alien technology as extraordinary, the gatekeepers set the bar so high that no evidence will ever be enough. They demand a photo of the alien pilot before they will even consider looking at the sensor data. Avi's struggle highlights a flaw in how we do science today. We have become risk-averse. Scientists spend their lives chasing grants and funding. To get funding, you must study things that are safe and guaranteed to produce results. Searching for extraterrestrial technology is high risk. If you find nothing, you have wasted years. So the system rewards those who walk the safe path and punishes those who walk into the jungle. But history tells us that the biggest breakthroughs come from the jungle. There is a profound sadness in this part of the story. It is the sadness of lost time. How many discoveries have we missed because we were too afraid to look? How many young students turned away from astronomy because they were told that searching for aliens is crazy? Avi Loeb continues to push. He founded the Galileo Project to build new telescopes, new eyes to look at the sky without prejudice. He is doing exactly what Galileo did 400 years ago, begging the world to just look. He accepts the loneliness. He accepts the insults. He does this because he believes that science is not about being right. It is about being curious. He often compares himself to a child. A child does not worry about tenure or reputation. A child picks up a strange shell on the beach and asks, "What is this?" The gatekeepers are the adults in the room, tired and cynical, telling the child to throw it away because it's just a rock. But the future of our species depends on the child. It depends on the willingness to be wrong, the willingness to be mocked, and the courage to stand alone in the face of the crowd. As we move toward the conclusion of this saga, we must ask ourselves, are we ready to look through the telescope, or are we simply waiting for the next Galileo to be evinced? The transition from October to November was not marked by loud alarms or breaking news alerts. Instead, it arrived with a quiet, rhythmic sense of patience. For weeks, the object had been lost to the glare of our star. From the perspective of Earth, it had travelled behind the Sun, entering a zone astronomers call a solar conjunction. During this time, even the most powerful eyes we have on the ground and in orbit were rendered temporarily blind. The light of the Sun is simply too overwhelming. It washes out the faint reflection of any small traveller passing near it. But orbits are clockwork, they are predictable, steady and reliable. We knew exactly when the geometry would shift, we knew exactly when the angle between the Sun, the object and the Earth would widen enough to let the darkness of space return. As the first week of November began, a collective hush fell over the scientific community. It was a comfortable vent, born of preparation rather than fear. In high-altitude observatories in chilly Hawaii and the Canary Islands, telescopes were already programmed. They were not scanning the entire sky. They were staring at a very specific small patch of the pre-dawn horizon. They were waiting for the curtain to lift. The atmosphere in these control rooms was distinct. There was no panic. There was no frantic typing or shouting. Instead, there was the soft hum of cooling fans, the smell of warm coffee, and the low murmurs of colleagues checking weather reports. The mood was one of deep curiosity. The world was about to see an old friend again, and everyone wanted to know how the journey around the Sun had changed it. The re-emergence was not a singular explosive event. It was a gradual unveiling. It began with the space-based telescopes, which did not have to wait for the Earth to rotate or for the atmosphere to clear. They caught the first glimpse. At first, the data was just a smear of pixels, a tiny imperfection against the background of stars. But as the hours passed and the object moved further from the sun's interference, the image sharpened. It was still there. It had survived the intense heat and the gravitational tides of its close approach. This moment, the first light after the blackout, was the moment of truth. This was the time to test the scenarios that theorists had debated for the last month. The first scenario was the cometary transformation. Many scientists expected that the intense heat of the sun would have caused the object to crack or vent gas. If it were made of ice and rock like a standard comet, the solar encounter should have been a violent event. We expected to see a long glowing tail of steam and dust stretching out behind it, illuminated by the sunlight. If this happened, the object would become a beautiful, harmless spectacle in the morning sky, a fuzzy ball of light, visible even to the naked eye. It would be a sign that nature was taking its course, melting a wanderer from the cold outer edges of the system. The second scenario was the solid state. In this version, the object was a dense metallic asteroid. If this were the case, it would emerge from behind the sun looking exactly the same as it did when it went in. It would be a single stubborn point of light. It would not have a tail. It would not have a cloud of gas. It would just be a rock, warm and silent, continuing on its path. This scenario would suggest a natural, albeit unusually sturdy composition. It would be a fascinating geological specimen, a survivor of the solar fire. Then there was the third scenario. This was the one that kept the astronomers awake, not with worry, but with a sense of wonder. This was the active return. In this scenario, the object would not just reflect sunlight, it would do something else. Perhaps its trajectory had shifted in a way that gravity alone could not explain. Perhaps the rhythmic pulsing of light, the signal we had detected months ago, would resume. Before the solar conjunction, the object had fallen silent. We did not know if the silence was permanent or if the object was simply conserving energy. If the radio telescopes began to pick up that steady artificial beat again, we would know that the object was not just a rock or a ball of ice. We would know it was still functioning. As the data began to flow down to the servers on Earth, the picture became clear. The images processed on the screens did not show a massive tail of gas. The object remained compact. It had not crumbled under the heat. It was solid. However, it was not just a dull rock. The light curve of the graph showing how bright the object was over time showed something elegant. The brightness was fluctuating smoothly. It was brighter, then dimmer, then brighter again in a slow, gentle cycle. This suggested rotation. The object was spinning. The heat of the sun had perhaps imparted a spin to it, like a child spinning a top. It was a graceful motion. More importantly, the colour of the object seemed to have shifted. Before the encounter, it was dark and reddish. Now the spectrometers indicated a surface that was slightly more reflective, perhaps polished by the solar wind, or changed by the extreme temperatures. It was gleaming. The global network of telescopes synchronized their findings. From the amateur astronomer in a backyard with a pair of binoculars to the lead scientist at the world's largest observatory, the feeling was shared. The object was intact. It was leaving the neighborhood of the sun and heading outward again, moving towards the orbit of Earth, but passing safely by. The anticipation shifted from, will it survive, to what is it saying now? The radio telescopes turned their giant dishes toward that point of light. They listened to the static of the universe filtering out the noise of the sun and the background radiation of the galaxy. They were searching for a pattern, and there, buried in the quiet hiss of space, a signal emerged. It was not a loud broadcast, it was soft, like a heartbeat returning after a long pause. It was slow and rhythmic, it did not feel threatening, it felt like a beacon. The emergence was complete. The object had stepped out of the fire and into the view of the world once more. It was not a monster and it was not a ghost. It was a traveller that had weathered the storm. As November progressed, the object would become clearer in the night sky, a steady point of light for anyone who looked up. The fear that had existed months ago had largely evaporated, replaced by a calm acceptance. We were sharing our solar system with a visitor. The tests and the scenarios had given us an answer. It was not a comet breaking apart, nor was it a dead rock. It was something durable, organised and persistent. The world watched not with held breath, but with open eyes. The mystery remained, but the panic was gone. We were ready to observe, to listen, and to understand what this silent Voyager intended to do next as it sailed through the quiet dark of the inner solar system. By March of the year 2026, the long darkness of the journey begins to break. We have travelled hundreds of millions of kilometres from the warmth of Earth leaving behind the rocky inner planets to approach the kingdom of giants. As our spacecraft glides silently through the vacuum, the target of our mission dominates the view, filling the entire window with a terrifying majesty. We have arrived at Jupiter. This is not merely a planet, it is a failed star, a massive ball of hydrogen and helium so large that 1,300 Earths could fit inside it. As we initiate the orbital insertion maneuver, the reality of the solar system's scale truly hits us. Back home, we think of mountains and oceans as big. Here, the Great Red Spot, a storm that has been raging for hundreds of years, is wide enough to swallow our entire home planet whole. The instruments on board begin to scream with data, though in the silence of space there is no sound. The radiation belts around Jupiter are intense, invisible rivers of charged particles that would fry unprotected electronics in seconds. We measure the magnetic field, which is thousands of times stronger than the one that protects Earth. We observe the swirling bands of clouds painted in shades of ammonia white, sulfur orange, and deep bruised browns. The winds here blow at speeds of hundreds of meters per second, faster than the strongest hurricane ever recorded in human history. But we are not just here to look at the gas giant, we are here for its children. Jupiter is like a miniature solar system of its own, possessing dozens of moons. Our focus turns to one in particular, Europa. As we swing past the massive gravity well of the planet, we train our sensors on this small icy world. It looks like a cracked eggshell, a white ball covered in reddish-brown lines. We know that beneath kilometers of ice frozen as hard as granite, there is a global ocean of liquid water. It contains more water than all of Earth's oceans combined. This brings us to the true heart of the mission, the question that has haunted humanity since we first looked up at the stars. Are we alone as we scan the ice of Europa for chemical signatures, for heat vents? For any sign of organic movement, we are faced with the two most profound possibilities in existence. As the science fiction writer Arthur C. Clarke once said, "Two possibilities exist, either we are alone in the universe or we are not. Both are equally terrifying." Let us consider the first possibility: we are not alone. Imagine the sensors pick up a trace of bacteria, or perhaps something more complex, swimming in the dark waters beneath the ice. It would not be little green men in spaceships, it would likely be microscopic. Yet the discovery would shatter every philosophy, religion, and history book back on Earth. It would mean that life is not a miracle unique to Earth, but a common rule of the universe. It would mean that in the billions of galaxies with their trillions of stars, life is everywhere. This is beautiful because it means the universe is alive, teeming with potential. But it is also terrifying. If life is common, it means we are not special. We are just another biological accident. It also raises the dark question: if life is common, why have we not heard from anyone else? Is there something out there that destroys civilizations before they can travel the stars? Finding life on Europa might be the first step in realizing we are swimming in a dangerous ocean. Now consider the second possibility: we are alone. Imagine we scan Europa, then Titan, then Enceladus, and we find nothing. Just cold, dead rock and ice. Imagine we travel for thousands of years and find only silence. This too is beautiful and terrifying. It is beautiful because it makes human life infinitely precious. If we are the only conscious beings in the universe, then we are the universe's way of experiencing itself. Every laugh, every dream, every piece of art, and every scientific discovery we make is the only time the universe has ever had a thought. But the terror of being alone is heavy. It implies a crushing responsibility. If we destroy ourselves through war, climate collapse, or negligence, then the light of consciousness goes out forever. The universe returns to blind, dumb silence. We are the sole guardians of the flame of life. The emptiness of the space around Jupiter, the sheer scale of the distance to the next star, amplifies this feeling of isolation. It makes you want to hold onto Earth tight and never let go. As the spacecraft continues its orbit, gathering data that will take scientists years to analyze, the perspective shifts. We look back toward the center of the solar system. From here, the sun is just a very bright star, not the blazing yellow disk we see from the ground. And Earth, from the orbit of Jupiter, Earth is almost invisible. It is a speck of dust suspended in a sunbeam. It is hard to believe that every human being who ever lived, every king and peasant, every hero and coward, lived out their lives on that tiny pixel of light. This rendezvous with Jupiter does more than give us data on gas composition or magnetic fields. It forces us to grow up. It forces us to look away from our mirror and out the window. When you stand next to a giant like Jupiter, you realize that our tribal squabbles, our borders, and our wars over resources are absurd. We are one single species riding a fragile life raft in a vast, dark, and indifferent ocean. The data stream ends for the day. The spacecraft enters the shadow of the giant planet. For a few hours there is no sun, only the faint light of the distant stars and the glowing auroras at Jupiter's poles, electric blue lights dancing in the dark created by the planet's magnetic fury. We continue to drift, carried by the laws of gravity designated by Isaac Newton centuries ago. We are far from home, yet we have never felt more connected to the grand machinery of nature. Whether we find microbes in the ice of Europa or simply more ice, the answer will change us. We push on, the engines fire silently adjusting our course. We are not stopping here. Jupiter is not the destination, it is the gateway. Beyond lies Saturn with its rings, the ice giants Uranus and Neptune, and the deep frozen scattered disk of the Kuiper Belt. The rendezvous is complete, but the search has just begun. We turn our antennas back toward the pale blue dot, sending our message across nearly 600 million kilometers of void. We are here, we are watching, and we are still exploring. The screens are dimming now. The data streams that once raced across the monitors like waterfalls of green numbers have slowed to a gentle trickle, and finally to a stop. The great telescopes that turn their giant glass eyes toward the darkness are resting. The hum of the cooling fans has faded away, leaving only the natural heavy silence of the night. Our journey with the visitor, known as 3i Atlas, has come to its end. Let your mind drift away from the math, away from the questions of speed and trajectory. Let go of the need to know the answers. The object is gone. It has crossed the invisible lines of our solar system, sailing past the cold gas giants, slipping through the empty spaces where the sun is just another bright star in a crowded sky. It is returning to the deep, endless ocean of the interstellar void. Take a deep breath in and let it out slowly. Imagine you are standing in a wide open field at night. The grass is cool beneath your feet. Above you the sky is a perfect dome of velvet black dusted with the diamond light of a billion stars. It is quiet here, the kind of quiet that wraps around your shoulders like a warm blanket. Think back just for a moment on the journey we took. It started with a surprise, a tiny anomaly in the data, a visitor from far away. We watched it dance around our sun, we watched it brighten and dim like a lighthouse spinning in the fog. We asked so many questions. Was it a rock? Was it a ball of ice? Was it a machine made by hands we will never shake? In the end, perhaps the answer does not matter. The mystery itself was the gift. For a few short weeks, the whole world looked up. We stopped looking down at our phones, our desks, and our busy streets. We looked up. We remembered that we live on a small blue marble floating in a vast, beautiful sea of darkness. Atlas was a mirror. When we looked at it, we saw our own curiosity reflected back. We saw our desire to reach out, to understand, to connect. It reminded us that the universe is not empty. It is full of movement. It is full of travelers. Now imagine that you are floating. You are weightless, safe and warm. You are drifting in that same space between the stars. There is no sound here, only a profound peace. The darkness is not scary, it is restful. It is the color of sleep. Think about the dust, the tiny particles that trailed behind the visitor. Scientists tell us a beautiful truth: we are made of this same dust. Every atom in your body, the iron in your blood, the calcium in your bones, the carbon in your breath. It was all cooked in the fiery hearts of ancient stars billions of years ago. When a star dies, it explodes and scatters its dust across the galaxy. That dust gathers together, swirls around, and eventually forms planets. It forms mountains, it forms oceans, and eventually it forms you. You are not just living in the universe, you are the universe. You are a piece of the cosmos that has woken up to look at itself. When you look at the night sky, you are looking at your ancestors. You are looking at your home. 3i Atlas was just a cousin, a distant relative passing by to say hello. It came from the same stardust that made you. It is made of the same ancient materials. It is returning to the dark, and you are returning to rest. Feel your body getting heavy now. Let your shoulders drop away from your ears. Unclench your jaw. Let your hands rest loosely by your sides. Feel the weight of gravity holding you gently, grounding you, keeping you safe. The object is now millions of miles away. It is traveling into the great silence. The great silence is not lonely. It is peaceful. It is the silence before the world began, and the silence that remains when the noise fades away. It is the silence of a library at night or a forest in winter when the snow falls. Let your thoughts slow down. Imagine your thoughts are like that distant object. Watch them drift by. Do not try to catch them. Just watch them float past you, getting smaller and smaller until they disappear into the dark. There is no rush anymore. The race is over. The calculation is finished. The sky is vast and patient. It has waited billions of years for this moment, and it will wait billions more. It has time. You have time. As 3i Atlas fades, it leaves behind a trail of calm. It leaves behind a feeling of unity. Under the night sky there are no borders. There are no countries. There is only one planet breathing together in the dark. We are all passengers on this same ship travelling around the sun, protected by the thin blue line of our atmosphere. You are part of this grand design. You belong here. You are just as important as the stars above. You are a child of the galaxy made of light and shadow. Now the darkness is getting softer. The silence is getting deeper. The stars are twinkling slowly like sleepy eyes closing one by one. Drift, float, rest. Imagine the object is singing a lullaby of silence as it travels. A song of low frequencies, a vibration that soothes every muscle in your body. The distance is growing, the quiet is growing. You are safe in the harbour of sleep, the night is your friend, the stars are your guardians. Let go of the story, let go of the words. There is only the rhythm of your breathing, in and out, slow and steady, like the tides of the cosmic ocean. Everything is okay, the universe is unfolding exactly as it should. You are exactly where you need to be. Resting, recovering, preparing to dream. Good night to the traveller in the dark, good night to the stars watching overhead. Good night to the noise and the hurry, good night to you. Sleep now, deep dreamless sleep, into the stardust, into the silence.